And have plenty of time. I'll be here until what, Monday morning, is it, Betty? So we have plenty of time. And I commend you all who have the endurance that you have. I left off talking about the solar perturbations, or the sun has this cycles every 7 years approximately where it does ups and downs. And I want to show you how that has an impact on radioactive carbon dating. And I should say how much I appreciate your previous speaker. He was really good. I sounded like a college professor. I think he's headed in that direction. But anyway, when we look at this slide, it talks about the radioactive carbon dating, which is very reliable, except what assumptions do you make? And of course, what we find out is such that when we talk about the half-life of a material, well, let me show you what a radioactive decay curve looks like without reading all of that. And then I hope I can change it to here, there. A radioactive decay curve looks like this. You start out with about 100% of the material, and as time goes on, it decays, and you can see about right here, for carbon, it takes about 5,600 years for half of it to decay. So those of you who are in radioactive stuff, you talk about half-lives a lot, and of course you can talk about half-lives and other things too. But we talk here about 50% of the stuff decays in about 5,500 to 5,700 years. So when we talk about the radioactive decay of carbon-14, we notice that carbon dating is used that way for historical times, and it can be very useful. However, even with such historical calibration, archaeologists do not regard carbon-14 dates as absolute because of frequent anomalies. That means things that can happen that you didn't know about. They rely more on dating methods that link into historical records. Outside the range of recorded history, calibration of the carbon-14 clock is not possible, and that's where we ended up in our last session. So I wanted to let you know that even when someone says this was dated by radioactive carbon dating, and you bring up the issue of, well, the solar cycles determine the amount of carbon-14 up in the higher level of the atmosphere, and that's how the trees take it in. And then when the trees die, the scientist goes and he examines the tree or fossil of any other kind to see how much radioactive carbon is there. And of course you see that when the decay happens, he calibrates this age based on how much radioactive carbon-14 is still there. Now, you don't need to be a rocket scientist to figure out if you were off by a little bit, and you're down here saying this looks like it's 40 to 50,000 years old, and of course if the error was just a little bit, just say like one of these bars, well, is the difference between 50,000 years and 15 or 20,000 years. If it's off by this much, oops, it's only 12,000 years. If it's off by that much, oh, it was actually 10,000 years. So when you bring these issues up, and I like to do this when people are talking about that, they go, oh, yeah, sure, that's right. And that's the end of the, unless the guy's out of it, of course. But that's why I wanted to show you the radioactive carbon dating issue. It's based on assumptions that either ignore the solar cycle, in which case honest scientists will say, yeah, we didn't even put that in there because we can't measure data we don't have, like I was showing you earlier. So that's one of the issues about the radioactive carbon. And I'm going to skip this Big Bang idea because people in churches do not like the word Big Bang, but I talked about this morning that when the universe, physicists and astronomers now agree that the universe was created in one big incident. Now the word bang was attached to it because that's the familiar thing we have. But we know that when God spoke and brought the universe into existence, it did not take millions of years for this to happen, to bring the universe into existence. But the age of the universe, how old it is not known to us, and let me show you why. Could someone type 356 into that thing right there? I think 356, just type in 356 and hit return. Yeah, hit return key, that ought to do it. Oh, that's okay. Then type in 364. Thank you. Thank you. school, they were talking this way. Of course, now, the new idea, it was created instantly. And of course, I said there's no bank, because there was nothing to bank. It's just the term they use. The other old idea is the universe is static. It maintains constant size. Now we believe it's expanding rapidly. And when I was, one of the things I had to do when I was the MLK physics professor of the year was to go and spend a whole day at a university, and the physics professors took me through, and they said it's not only expanding rapidly, but new information from the Hubble Space Telescope shows that the rate of expansion is increasing. See, at one time we thought that the universe was expanding from the big explosion, and it would expand, and then gravity would put it back in on. Then gravity would pull it back in on itself, and it would collapse, and that would be it. But now it's expanding even more rapidly because they can measure this by infrared shift in the spectrum. The old idea was expansion. Well, I said that already, didn't I? So the rate of expansion is accelerating, and the farther away, the faster. The old idea, Edwin Hubble calculated the age of the universe to be about 2 billion years old in 1929. So by now, it would be a little older, wouldn't it? Well, the NASA estimates the age of the universe to be about 3.5 billion years in 1999. So, I hate to say it, but in those few years, the age of the universe has really improved. So this shows the certainty of scientific calculations. Seeing is believing in the old days. Now we know that about 95% of the universe is dark matter. You can't see it. I also want to add right here, I don't have a slide to show this, but as the universe expands and the expansion goes more rapidly, I attended a lecture by a distinguished scientist who pointed out that at the very edge of what we can see, that is what the Hubble Space Telescope can see, the outer edge, these are going so fast right now, we know by the shift in the light spectrum. Now, when they get to go a little faster, they'll be going so fast until the light from them will never reach us. You understand what I'm saying? I see your hand. Yes.
What exactly is dark matter?
Okay, we're living on one right now. See, it sounds like a big, and I used to ask that question because I went, what are they talking about? But basically what they're saying is, when they look out into the great expanse of space, you can see the stars that emit light. You can see the big clouds that still scatter light. But the universe is behaving in such a way, like when we discovered Pluto, it wasn't because we looked out and saw Pluto, it was because we found that the orbits of the nearby planets were behaving not according to calculations. So we go, well, there's got to be something out there pulling on them. And we looked where the thing was supposed to be, and there it was. And it was called a planet for about, 80 years? Now it's been demoted to no longer being a planet because it's too small. Again, science at work. So in the case of dark matter, when they measure the expansion rate of the universe and find out there's some things that are not behaving the way they should be out there, because you and I pay taxes to pay these guys to sit and look all night and to make these calculations. So when we say, oh, something must be pulling on that thing, and we conclude it's matter that we cannot see with our telescope. So it's dark. So we're living on a piece of dark matter right now because it doesn't give off radiation like the sun does.